This video will discuss how column chromatography works, industrial applications of column chromatography, and how to set up a column for separation.
So, let's see how column chromatography works. Starting off, you'll need a glass column with a screen at the bottom to prevent your stationary phase from eluting out. There is also a stopcock at the end to control the flow rate of your column. You can use a beaker or vial to recover your fraction samples. The stationary phase, or packing, typically consists of a very polar adsorbent such as silica or alumina. Several parameters such as the size or polarity of your particle are critical for the efficiency of your separation. You'll need a mobile phase, also known as your solvent, that will carry the analyte through the column. The analytes are the compounds you want to separate. Selection of your solvent is based on the compatibility and polarity of your compound, so make sure you do your research into what works. When the mobile phase is carried through the column, the analytes that are dissolved in it can adsorb with the stationary phase, which is the cause of separation. Let's say our analyte is a mixture of methylene blue and methyl orange. It's important to ensure that your stationary phase does not dry out, so make sure there was always some solvent in your column that is above your packing. When we introduce this mixture to the column, you should begin to observe separation. As the elution proceeds over time, you may begin to observe separation of the dyes. This separation is typically due to the differences of polarity of the compound and stationary phase. In this example, we see that after 30 seconds, the methylene blue elutes down the column faster than the methyl orange. We can conclude that the methyl orange has a stronger attraction for the absorbent, thus making it more polar. As the elution proceeds, we can recover the fractions from the column, which can then be analyzed in a spectrophotometer.
Column chromatography is used on a large scale in the pharmaceutical, petrochemical, and food industries to separate a variety of compounds. For example, in the food industry, sugar and molasses are separated using column chromatography. In the pharmaceutical industry, column chromatography is used to perform difficult separations of chiral molecules. For smaller scale processes, a batch chromatography process can be used. For large-scale or continuous processes, though, such as in the separation of sugar and molasses, a continuous setup is needed. Next, we'll talk about how to set up a chromatography column. The materials we used were methylene blue dye, methyl orange dye, ethanol, water, silica gel, and alumina particles. To pack the column, silica and the solvent, ethanol, are mixed together. The mixture is swirled to form a slurry. After swirling, the slurry is quickly poured into the column. The particles are allowed to settle, and the excess solvent is drained off. When the solvent level is just above the top of the packing, the sample is loaded into the column. Then, more solvent is poured over the sample until the column is full. Now, separation can occur. To speed up the process, pressure is applied to the column to force the mobile phase to elute more quickly. When silica packing is used, the orange dye reaches the bottom of the column first, while the blue dye stays near the top. When we use alumina packing, the opposite occurs. The blue dye travels through the column much more quickly than the orange dye. This happens because of differing attractions between the dyes and the packing.